Alrighty, we'll kick off. Good morning, everyone. My name is Gina, and I am a manager on ARENA's knowledge sharing team. I will be emceeing today's ARENA Insights webinar on grid forming inverters. Please note that this webinar is being recorded, and we will be posting this on the Knowledge Bank in the coming weeks. Thank you so much for taking the time in your day to join us this morning. Today, we're presenting insights from ARENA's storage projects with advanced inverter capability. We will have presentations from a broad range of industry and academic experts, and then we will go into a facilitated Q&A discussion with all of our presenters. Again, I invite you all to explore the Zoom Q&A function that is located at the bottom of your screen. Feel free to send questions throughout the presentations, and we will aim to address them in the final Q&A session. But first, we have ARENA's CEO, Darren Miller, with us to make some opening remarks. So over to you, Darren.
Thanks, Gina, and good morning, everybody. I'd like to start today by acknowledging the traditional custodians of the countries on which we will meet today. I'm on Gadigal land today in Sydney, and I pay my respects to the Gadigal people of the Eora Nation. And I extend that respect to all First Nations people who are with us today, and indeed to the First Nations people whose lands on which you're all meeting. So by way of introduction, I just wanted to say that we all know that advanced inverters with grid forming capabilities are increasingly going to play an important role in the energy transition. We can't get to those high share of renewable, variable renewables that we all desire, and which the government has in its sights if we don't have the technical capabilities to support the grid with new technology as coal and gas comes out of the system. So in particular, we know that advanced inverters can play a role in providing inertia services and system strength. And usually a non-engineer has to say, I'm not an engineer. So I will definitely say that in terms of understanding exactly what system strength is and all these capabilities are, is really up to the system operators and the engineers. We in the economic framework or in general society place a heavy reliance on the work that we're all doing here, that many of you are involved in being able to prove to us in the real world that these services can be provided by the new technology and give us that real confidence that we can remove coal in particular rapidly out of the system, and that gas will increasingly also play a minority role in supporting the system. So today's webinar is really just an opportunity for us to all share real world insights from the battery storage projects with advanced inverter capabilities that are already in the field or about to operate. And in particular, we'll discuss some of the key challenges faced and the lessons learned from the advanced inverter projects that are either connecting or looking to connect, have connected or will connect to the network shortly. ARENA's played an important role in this space. We've invested nearly $40 million in battery storage projects with advanced inverter capabilities. And through our large-scale battery round that is currently in the assessment process, we'll look to invest a further $100 million into large-scale projects, specifically with advanced inverters with grid forming capabilities. We've also recently provided $1 million grant to support Monash University's research into grid forming inverters, including inertia and market design for storage. So I'm going to leave it to the experts in a minute and to all of you to get into the day. I'd just like to thank my team in particular, to Dan Sturrock and Carl Christensen in our BD&T team for coming up with this idea to host this webinar on grid forming inverters, and particularly also to Kate O'Callaghan and Gina Zeng for bringing this webinar to life. And indeed to all of you for your time, which is valuable, and I hope you get something meaningful out of it, and thank you for your participation. So back to you, Gina. Thanks.
Thank you, Darren. I will now introduce our first speaker for this webinar, Chris Mock from AEMO. Chris is a principal engineer at AEMO and is currently leading the development of AEMO's white paper on advanced inverters. Over to you, Chris.
Thanks very much, Gina, and hello, everyone. I'll apologise in advance. I am losing my voice, so I'll keep this fairly short and sweet. But look, today I'd just like to present to you on a number of actions that we have underway underneath our engineering framework banner that we're taking forward this financial year. So just as a refresher for those who haven't come across it before, AEMO's engineering framework, it really seeks to facilitate this orderly transition to a secure and efficient future NEM. And it's helping to define some of the technical and engineering requirements that we're going to need in order to support future operational conditions. So we published an initial roadmap for the engineering framework in December 2021, and this provides a catalogue of over 300 potential sort of gaps in the activities that are needed to support this transition. And it also highlights where urgent decision-making is going to be needed to support the best approach for these power system transition activities. And this is an excerpt of that section of the report. And so you can see that as the synchronous generation fleet exits, new sources are going to need to be found for the essential power system capabilities, such as system strength and inertia, that these assets are currently providing. And so we really do see a need for both advanced inverters and synchronous condensers in meeting these future essential system service requirements, and the development of efficient pathways towards deploying both of these needs to progress in parallel. And you can see in the bottom left there that this action that we've called out the need to trial and enable an incentivized advanced inverter deployment in the near term. Next slide, please. So in June this year, we published an engineering framework priority actions report, and that takes a prioritised subset of those 300 gaps and turns them into tangible actions. We were asked to develop a top 10. We made it to a top 46. I think that highlights the sort of complexity and the urgency of all this work. And so we did manage to get 12 of those key actions to map to key decisions on approach from the initial roadmap. And again, an excerpt of those here that maps to the previous slide. So the first three of these I feel are quite relevant to advanced inverters. So action A1, this speaks to the revised, sorry, you've back one slide, yeah, perfect, thank you. So the revised system strength framework that considers ways to efficiently deliver system strength with a technology neutral approach. And AEMO is actually currently consulting on the methodology and assessment guidelines for this piece. So that's closing on August 19th. I'd encourage people to have a look at that if they're interested. The second one on the list there, A2, AEMO is progressing a number of power system studies this year that really seek to assess the power system security at times of 100% renewable energy penetration. And that's so that we can take a future back approach and identify forthcoming stability issues rather than incrementally locating those as we move along penetration rates. Now I'll speak to action A3 a little bit later, but we are seeking to collaboratively define the necessary power system support capabilities for grid forming inverters to help guide OEMs and developers, of which I see a number are on the pool today. Okay, next slide, thanks. So here are sort of three grid forming actions that out of the 46 in our report that directly relate to grid forming inverters. And so again, action A3, to begin this process of defining these necessary power system support capabilities, we're proposing to collaboratively develop what we're deeming a voluntary specification for grid forming inverters. And I'll go into a bit more detail on that later. Action A14 is really a call out to the importance of ARENA's large-scale battery storage funding round. It's absolutely critical that we can demonstrate the capabilities of this technology at scale and capture this current window of opportunity to incorporate grid forming technology on the fleet of currently proposed projects. Last on the list there, A27, this one is there to assist developers of grid forming batteries who are seeking to connect under the current day rules. And AEMO will be publishing a short fact sheet this year to help clarify how grid forming inverters will be assessed and to provide some pointers as to where close attention to design and tuning is going to be needed. There's more detail on this on the next slide, thanks. And so developers have been coming to us and seeking further information on how these projects will be assessed under current rules. And so we're drafting this fact sheet to sort of highlight clauses of the NER where we think that focused attention and early discussion are going to be needed between proponents, AEMO, NSPs, and that's based on our learnings from previous connection applications for ARENA-funded projects. And so drafting for this has begun. We do need NSP feedback, and that's a really critical element of this. And so we do have a round still to go of feedback with the NSPs, a little while off release, but very much drafting is underway. And to date, the focus has been on navigating the regulations as they stand today, linking across to reform work where it's relevant, rather than necessarily promoting change through this venue of the fact sheet. It's worth noting, though, that some of the clauses of the NER were not necessarily developed with specific consideration of grid-forming inverters in mind. And so this report will highlight where early discussion is going to be really critical with the NSP and AEMO in order to ensure that plant tuning sort of meets the requirements of the rules, as well as meets the needs of your own plant and system design. There's a reference here on our AEMO's submission to a recent rule change request that's with the AMC at the moment on efficient reactive current access standards for inverter-based resources. That's a combined request from a couple of proponents. The number for that is there. And I'd recommend that people have a look at that if they have a chance and like to get into some of the technical detail, because it does show some clauses where we feel that the wording could be improved to cater better for grid-forming inverters. So please do take a look at that if you'd like to dig a little deeper. Next slide, please. And so this takes us back to this voluntary specification. And, AEMO's white paper, it highlighted that an absence of clear specifications make it quite challenging for developers to specify the requirements from OEMs and for OEMs to define their inverter offerings. And so we feel that aligning on views and the definitions, the capabilities, the power system needs really needs to be that first step. And so we're seeking to collaboratively develop this voluntary specification to begin this alignment process. The specification will need to consider both technical and operational requirements. I mean, for example, we'll need to cover expected behaviour from grid-forming inverters under particular system conditions, as well as considering operational matters such as any headroom that's going to be required in order to enable that meaningful delivery of capabilities such as system strength and inertia. And so the output of this work can then be used to inform future regulatory change processes, such as the ESB's Essential System Services Review, reform and the Access Standards Review. And look, I really do see the process of developing this voluntary specification as important as the specification itself. Getting everybody in a room to discuss these points is the critical part. It's worth noting that other jurisdictions have taken a similar approach to this. In the UK, National Grid's GC 137, which is now non-mandatory part of the UK Grid Code, they took that approach of a non-mandatory specification, which was then used in a formal sense as part of a procurement process for their Stability Pathfinder program. And that was there to procure network services from grid-forming batteries, amongst other technologies. And so this work's expected to run over the later part of this calendar year. Please do reach out if this is of interest and you'd like to be involved. Our email address is on the screen there. That's all my voice can handle. That's it from me today. Thank you.
Thank you, Chris. Next, we'll have Elise Green from Tesla. Elise is a project engineer at Tesla and ran the commissioning tests for the implementation of virtual machine mode at Hornsdale Power Reserve expansion and is planning the deployment of this feature at other battery sites. Over to you, Elise.
Thank you, Gina. Yeah, as Gina mentioned, I'm a project engineer working with Tesla, and I've primarily been involved with utility scale batteries. So I've been involved with this project at Hornsdale, implementing and commissioning the first grid forming mode, or virtual machine mode, as we call it at Tesla, at the inaugural large scale site in Australia. So in this presentation, I was planning to talk through some of the practical elements of what's been involved behind the scenes to get virtual machine mode approved on the site. So this first slide is just intended as an overview of the site that was used for this first large scale implementation of what I'm now going to call VMM, virtual machine mode. And that's, of course, Hornsdale Power Reserve, owned by NEON. It's a 150 megawatt site situated in Jamestown, South Australia. And virtual machine mode commissioning was completed last month. So the site is now operating with virtual machine mode switched on. Next slide, please. So this slide is a quick synopsis of the journey that it's taken to implement virtual machine mode at Hornsdale. So it all began back in December 2019 when NEON secured funding to expand Hornsdale BESS and implement virtual machine mode. So that funding was joint funding from South Australian Government's Grid Scale Storage Fund and ARENA's Advancing Renewables program. So by September 2020, Hornsdale expansion was complete and the site was expanded from 100 megawatts to 150. So then began the journey for Tesla to kind of prove that our virtual machine mode feature worked in the way that we said it would, in providing grid forming mode from an inverter. So that was through a mix of lab testing, some trials on the site, and then of course the 539 studies. So just a quick summary of the 539 study is of course the clause set out in the NER, which must be followed when altering a generating system. Requires significant modelling studies of various scenarios to show how the alteration of the plant will affect the existing GPS. So between September 2021 and June 2022, the interconnection and studies and package were under review, and the performance requirements of the plant with virtual machine mode on was under negotiation. That was agreed by June 2022, and last month we rolled out the feature across the site, undertook the commissioning or hold point testing and model validation, and now the site is running with grid forming mode switched on. Next slide, please. So I know some of this has been covered in previous ARENA presentations, but I think it's worth doing a recap of exactly what virtual machine mode is. Then I'll dive into more details of the actual Hornsdale project. So this slide is intended as a schematic representation of how the inverter works. So the picture in yellow on the left represents a standard architecture for an inverter-based generator. So it's really a current source that provides real and reactive power in response to direct commands or in response to market conditions and network health. On the right-hand side in the blue box is the machine or grid forming element. When operating in virtual machine mode, this grid forming element operates in parallel with the grid following one. So it's important to note that this is not a new hardware requirement. Tesla's inverters are virtual machine mode capable, and the feature is enabled by just a settings change. So when both of these elements are operating in parallel, the resulting output provides the same real and reactive power dispatch services for standard grid following modes, along with the grid stabilizing services made available by the virtual machine element. So the system can respond at high speed to produce active power response proportional to the rate of change of frequency following some network event, or produce reactive power to improve the voltage waveform. So as we see the retirement of more fossil fuel-based synchronous generators, we're also seeing the loss of grid inertia, or in other words, the mechanical energy that heavy rotating machines hold that gives them the momentum to kind of ride through disturbances. So it's become essential that these grid stabilizing services can be provided by inverter-based technologies. And yeah, I guess that's why this Hornsdale project was particularly exciting. Next slide, please. So I now spend a moment talking about the works we did in order to get approval for this virtual machine mode feature before diving into the commissioning activities themselves. So as I pointed out in the earlier timeline slide, in order to build confidence around the machine feature, we needed to show how it responded to various grid events. Obviously, this is going to be pretty difficult in an actual grid connected installation because under normal network conditions, virtual machine mode is not really having any effect. It's really just running in the grid following element. So to demonstrate its operation would need to see a real grid event, and it would take a very long time to observe all those scenarios that need to be shown on the network. So instead we do a kind of lab demonstration testing called hardware in loop or hill testing. So this is a mock testing technique where we set up a device that can inject signals into the inverter under test that represent a fault scenario. So we tested a lot of different plausible grid disturbances from kind of frequency disturbances to bus angle shifts and grid fault scenarios. The figure on the right is just an example of one of those results. So this is a one phase to ground fault. So imagine something blowing over a transmission line during a storm. And in that case would see a certain voltage signature on the network, which is the injected power signal into the inverter. So the purpose of the hill test is to show physically how the inverter responds to such a condition, and then apply the same condition to the model to validate that our models accurately predict the real hardware's response. So in that graph, you can see there's a blue line for the actual lab test results and the green line for the modelled results. So this is a really close match, which is a good result. Next slide, please. So the next step in verifying virtual machine mode was the trial at Hornsdale. So we enabled virtual machine mode in 2 of the 296 inverters. And the 2 graphs on the right show the difference between the plain grid following response and the machine mode enabled response. So the one on the top is the whole site response. Given the portion of inverters with virtual machine mode on was so low, this is pretty much representative of a current source response. So you can see that the peak in active power, which is the orange line, corresponded to the maximum frequency deviation in purple line. The lower graph is taken from a meter at the inverter terminals of one of the machine mode enabled inverters. So with this one, you can see the response is different, where the peak in active power corresponds to the highest rate of change of frequency. So you can see that in that inverter injects power during the decline of frequency to help raise the frequency nadir, or the minimum frequency, and provide stabilization to support recovery prior to the frequency departing the deadband. So much quicker response than your traditional frequency watt response. Yeah, so this is evidence of the grid stabilizing features in action. Next slide, please. Yeah, now I'll move on to the most recent milestone, which was undertaking and passing the commissioning or hold point testing at Hornsdale. So hold point testing is aimed to demonstrate that the BESS can comply to the connection agreement, or in this case, the change connection agreement, to prove the accuracy of the model upon which the agreement was based. So the commissioning test in this case was conducted in 2 rounds. The first hold point was the capacity was restricted to 50 megawatts, and in the second hold point, the whole site was enabled with virtual machine mode, and its full 150 megawatt capacity was tested. So the test included real power steps, voltage control steps, and an external voltage disturbance test. And I've put in a little bit more information here on the external voltage disturbance test. Just, yeah, I thought it might be interesting to show the scale of equipment we're switching to kind of create these scenarios where we can demonstrate the machine mode acting. So what we did was energized a transformer to a nearby wind farm, which led to a inrush current, and that was kind of observed as a voltage disturbance on the 275 kV bus, which is shared with the BESS point of connection. So this voltage disturbance, you can see in the red in 0.3, was observed and echoed into the inverter terminals of the BESS, inducing that machine response. So on the next slide, yeah, this is, I guess, the exciting bit for us, which is that we observed that voltage dip. There's a very quick voltage dip at the inverter terminals, and the corresponding reactive current output of the inverters, which is evidence again of the machine mode response in the reactive power responding to clean the voltage waveform. Yeah, so this is what it's all about, really. Yeah, next slide. So yeah, as we can see from the ISP forecast chart on the right-hand side, the proportion of traditional fossil fuel-based synchronous generators in the NEM is set to decrease substantially, as we all know. And there's a need for inverter-based technologies to step up and provide the grid stabilizing services that will allow their penetration to continue to grow. So this slide is really just to show a illustration of why this milestone at Hornsdale is particularly significant and exciting in what it's achieved in terms of accelerating the world's transition to renewable energy. The project's been an amazing initiative supported by South Australian Government and ARENA, and has seen Neoen, Tesla, AEMO and Electronet working closely together. And it's ultimately led to the first large-scale demonstration of advanced inverter technology in Australia. And with the project pipeline we're seeing, it's clearly paved the way for many more. So yeah, an exciting time for the industry, I think. Next slide. And, yeah, that's all from me. Thank you, Gina.
Thanks, Elise. Next, we will have Sam from Edify. Sam is the head of technology and asset management for Edify and recently led the development of the Darlington Point battery. Thank you, Sam. Take it away.
No worries. Thanks, Gina. Yeah, so look, I'm going to talk about the Darlington Point energy storage system, which is a project which we've recently closed. It's currently under construction at Darlington Point. If you just jump to the next slide, please. So look, I thought I'd start just by talking, I guess, a little bit about what started us on the journey of thinking about system strength. So it really all started when we were developing the Darlington Point solar farm, which now the battery is being co-located next to. And so when we were developing that farm and going through the connection process, we sort of ran into the system strength remediation process. I think we were one of the earlier solar farms to sort of for this to come up during the connection process after those rules came in. And as a result, we ended up installing sort of two 42 MVAh synchronous condensers in the southwest of New South Wales. And so that got us thinking, I guess, after completing that project, what does this mean for our future projects? Is asynchronous condensers, are they sort of the new accessory to every solar farm? Do we just need to factor those in as a sort of a grid stabilizing device for all our new developments? And if you jump to the next slide, and sort of part of our thinking was, well, what does the network look like? This is a sort of a snapshot from one of the AEMO maps that they provide with the sort of the colors indicating the system strength, with red obviously being low. And I think just looking at this map and looking at, I guess, the priority zones for developing renewable energy, some of the reses are shown there, and the locations, I guess, in particular of our projects, I think it sort of occurred to us that, yeah, look, most of our projects are in low system strength zones. So that was sort of pushing us towards needing these remediation schemes. I think, as Elise just pointed out, just the announced retirements and the transition that we're on, the level of rotating generation is only going to get less. And I think we're seeing it roughly half by 2036, just based on the current announcements. And we had this battery planned at Darlington Point, and it occurred to us that if we just connect that with grid following inverters, we're actually going to probably need a system strength remediation solution to that as well. And so we thought, oh, what's the solution to this? And that was to basically look at grid forming inverters. And if you jump to the next slide, please. So that was really how the Darlington Point energy storage system in its sort of current form was, I guess, the idea for it was seeded. So we thought we need a system strength remediation solution here. Batteries can do it. And I think they actually have a lot of advantage over synchronous condensers, mainly that they can provide energy and active power. So they can operate as a normal battery, and this system strength is just sort of an inherent service provided while they're operating. So they've got a lot of advantages. For the project, we've selected the Tesla Megapack 2 technology, so very similar to what Elise was outlining before at Hornsdale with the virtual machine mode. I think the difference between our project, I guess, is that we conceived it this way from day one. So we went through the connection process 534A under the sort of existing rules with grid forming right from day one, and we'll switch it on during our initial commissioning as well. The current status of the project, I guess, as I mentioned, we're under construction, and we'll be looking to commission sort of around early to mid next year. If you jump to the next slide. So look, I thought I'd share a little bit about our learnings around going through the connection process with the grid firming inverters. Look, a lot of people have asked us, look, how's this been done? How do the rules apply to it? Do the rules currently allow you to connect grid forming inverters? And I think the answer is yes. As sort of Chris pointed out before, they'll be publishing some sort of guidelines on it, but I think the existing process, it's technology agnostic, so that the process for connecting it is actually exactly the same as any other generator. I think that the generator performance standards, I think they do need to be tweaked to be sort of specific to grid forming inverters compared to what you might negotiate for a grid following implant, but the templates don't prohibit this happening at the current time. And I think the fundamentals to success are the same. So yeah, having a very robust model that can pass the DMAC, can pass all the benchmarking. I think that remains the same for grid forming. That's real key. And I think having a stable response, I think it's important through this whole process to keep I guess to focus less on the performance standards, I think, and focus on what the network needs. I think these grid forming inverters, that they can benefit the network. And as I'll sort of outline in a bit, there is a bit of trade-off in the tuning process. I think keeping that kind of end goal of providing maximum stability for the network, I think will keep you in good stead in terms of getting the right outcome in terms of the performance standards. And just, I guess, in terms of time frame as well, I think we didn't see any difference in terms of the time frame for connecting grid forming inverters. In fact, I think, yeah, because we didn't have that sort of second round with requiring a system strength remediation scheme, it actually probably avoided some time in the connection process. Next slide, please. Yes, look, as I mentioned before, I think, yeah, a lot of people often ask me, oh, is it grid forming or is it not? And I mean, I think that the reality is that the grid forming, it's not a yes or no answer. I think it's sort of this degrees to which things are grid forming. And so the fact that you can tune this technology with settings means that you can sort of have them anywhere on this scale from sort of 0% to 100% grid forming. It's not this yes or no type answer. And so this is a huge benefit of grid forming inverters compared to conventional technologies, but it also is a challenge because it just gives you so many options of how you tune it when you're going through that connection process. And it's often confusing as to what should I actually be focusing, what's the best outcome. And probably the biggest sort of trade-off that we saw is against the rise in settling time versus stabilizing network oscillations. And I've shown a few of sort of the plots of responses there. One in a strong grid situation, a high fault level, and one with a weak grid, a low fault level. And you can see that, I guess, in the strong grid, there's a marked difference between the settling time and the rise time. And in the weak grid also, but I think in the weak grid, you can also see the difference between the level of oscillations and how quickly the oscillations are damped. And I guess what we found is that there's this real trade-off. And I think the focus needs to be about, well, what's the benefit that these can bring to the network? What does the network actually need in this location? And I think what we found is tuning it for our location, it was a weak grid. And the focus for us was around stabilizing network oscillations. And so there was some trade-off in terms of rise of settling time. But I think like going through this process, engaging with AEMO was really important to understand what they wanted to see in the network. And I think by doing that at the right time early enough, we're able to sort of jointly come up with tuning, which sort of maximize the benefit of this system to the network, but also allow us to agree performance standards that sort of suited that response. If you jump to the next slide. So yeah, look, I've talked about a lot of these a lot of the trade-offs here. Yeah, we found, I guess, there was a need, we found in situations that the rise and settling times that we talked about were challenged in the automatic access standards. And I think part of this is that there's so many network scenarios that you can analyze these days. So that was another sort of important issue to engage with AEMO on. Sort of there are this endless sort of number of network scenarios, but I think you need to be realistic and assess ones that are genuinely possible in that area of the network. These plots on the right-hand side, I guess, are trying to demonstrate another approach that we took, and that was really keeping the ultimate goal in line, which was providing stability to other renewable generators connecting in the region. And so to do that, I guess we took the studies that we did a little bit further, and in a SMIB model, we set up the grid forming BESS next to a typical grid following solar farm that we just introduced into the network. And so part of the studies was all like, this is the real problem on the network. How is our BESS helping that? And these lines sort of represent a sort of a range of different settings that we could use with the grid forming inverters. And you can see that in some situations, the grid following inverters actually trip, and sort of in the other scenarios, there's varying levels or varying degrees to how quickly the oscillations are damped. So I think this was a really important aspect of the studies, actually taking it further and saying, okay, what's the actual problem we're trying to solve here? And what impact are the settings having on stabilizing sort of existing oscillations in the network? Jump to the next slide, please. So this is just a little bit of how does it fit into the existing system strength framework? So, I mean, I think the same system strength framework that you apply to any generator connecting applies to these. So we undertook a preliminary impact assessment. I think they were considered inverter-based resources for that. So it did trigger a full impact assessment for our project. But the project went through that full impact assessment, found that no remediation solution was required. And in fact found that it was actually benefiting the network. So some of the existing issues in the network were being improved by the presence of this plan. And so we're able to pass through that process quite quickly. And then I think the next part of the question, which I sort of just touched on before, is, well, can the BESS actually stabilize additional grid following plan? And by how much? So as I mentioned, we set up some specific studies around this, connecting the grid following solar plan in parallel to the BESS, just to see the impact of that. We modeled it without the grid forming inverter first, and I think we did see, or we tuned it to ensure there were stability issues before that, and then we've brought on the grid forming BESS. And what the results were very, I guess, very impressed with, or they're very positive, and we found that sort of the 150 megawatt BESS could stabilize of the order of greater than 500 megawatts worth of solar at this location. So they were having a significant ability to provide sort of system strength remediation for other plants. Next slide. So this is just a sort of a few of the conclusions from our process today. Firstly, look, there's no reason that we can't be connecting grid forming inverters currently. The connection rules framework apply for that. I think Chris outlined some guidance that will be published by AEMO soon. In terms of timing, I think the fact that the grid forming BESSs are stabilizing the network, not introducing additional problems, I think can make the assessment process quicker. I think part of the issue with timing of our existing connection process is that everything's sort of resting on a knife edge in the grid at the moment. So hopefully this can help. And look, I think in connecting more of these at scale, it's important to accelerate learning. I think as we've gone through this process, I think we've helped working with AEMO to sort of define how grid forming inverters can fit into the current GPS. And so I think, doing that again, a number of times, different locations at scale is important. And as I mentioned, I think, working with AEMO early and sort of focusing on the specific needs of the network at that location is really important. I think next slide, or is that? That's the end. All right. No, thanks everyone.
Thanks, Sam. Next, as you guys will have got a sneak peek, is Dr. Baru Bohani from Monash University. Dr. Baru is a senior lecturer at Monash and director of the Grid Innovation Hub with a research focus on power electric conversions and grid integration of renewable resources. Over to you.
Thank you so much, Ina, for the introduction. Welcome everyone to this presentation. Unlike the previous presentations that you've seen today, which are focused on energy storage technologies and batteries actually for providing grid forming capability, I would like to talk a little bit about grid forming capabilities for renewable energy farms, as I guess this will become the norm as we integrate more renewables into the grid. Well, currently, I believe there isn't really much examples of grid integration of renewable energy farms with grid forming capabilities, but there is a lot of value in looking at grid forming capabilities for farms because you already have this energy resource that can, instead of being a problem for you, can be part of the solution. So I would like to talk a little bit about how this potentially can happen. Well, there's no secret, I guess, that we are going through this transition, and 60% of our synchronous generators are going to retire by 2030. We are hoping to have 100% of renewables by 2025, and we know that IBRs are fundamentally different from synchronous generators. So they have faster dynamics, they've got fast switching semiconductor devices, advanced digital controllers. All of them can give them a very distinct and different behavior compared to electromechanically coupled synchronous generators to the network. So the mixture of these IBRs and synchronous generators in the future will be very challenging, and we are changing the fundamentals of the grid by introducing more IBR. So we need to think differently to see how we can integrate more renewables into the grid without challenging our grid security. Next slide, please. So the challenge of the transition, I believe the power system requirements developed by AEMO back in 2020 actually outlined the challenges and problems of the transition pretty well by retiring more and more synchronous generators and the limitations that we've got in the IBRs. There are quite a lot of challenges that we will see in coming years. And if we are going to get it right, we need to have the IBRs to provide quite a number of services as outlined in the right. Particularly, IBRs need to connect to very weak parts of the network. As we just saw in previous presentations, quite a lot of renewable energy zones are located in weak parts of the network. So we need to make sure our IBRs can connect there. Supporting system security is another service that we need IBRs to provide, island operation, and finally system restart. So all of these, we're hoping that IBRs can provide for us, either in the form of battery energy storage systems or farms in the future. Next slide, please. Well, here I would like to very briefly talk about the two technologies. You probably know them already, but we've got grid following and grid forming inverters, and grid following inverters currently are the dominant type of IBRs in our network. They need to have a stable voltage at the point of connection and get synchronized with that voltage using a PLL, and often you can look at them as a current source. So you need a PLL to sense the voltage at the point of connection, and based on that sensed voltage, you will extract the frequency and phase angle of the point of connection, the voltage at the point of connection, and based on that, you can inject real reactive power. So essentially, you can look at them as a current source. But the grid forming inverters, on the other hand, they do not need to have actually a PLL to get synchronized to the grid. They are power synchronized, meaning that they can instantaneously sense any changes in the network, and it can help them to work in very weak parts of the network for two reasons. One is that they are not dependent on an external voltage source, and meaning that there isn't any PLL, and PLLs are typically the source of instability in weak networks. And also they themselves form the voltage at the point of connection. So they've got that advantage of getting connected to very weak networks. Next slide, please. Now, the existing solutions that we've got, as we saw in previous presentations, dominantly we are focusing on battery energy storage systems at the DC side of our grid forming inverters. So often we've got the DC side only connected to the battery, and then we are able to provide the services that we require, including inertia or any sort of damping that we want, any sort of virtuous synchronous generator that we want to implement, which makes it a little bit easier. Next slide, please. Because having only the energy storage at your DC side will give you less variables to control. There are quite a few examples of BESS-based grid forming inverters around the world. I guess the list is increasing these days. These are just 3 examples. I guess there is one in the right, the Darlington battery in South Australia, but we also have other batteries in South Australia. Quite a lot of them are coming online. So in future years, we'll be having a lot of battery energy storage systems based on grid forming inverters. Next slide, please. Now, when you're going to control your battery energy storage system based GFMIs, there are a number of variables that you need to control. So essentially, you would be controlling the real reactive power using a primary control loop. The primary control loop will then give you the frequency that you need for your system, for your control system, unlike grid following inverters that require the PLL to do so. You've got a PCC voltage control, which receives the references from the primary loop, and then would generate the current references of your inverter current control loop. So these are the variables that you typically use to control your battery energy storage system-based GFMIs. And there are not many of them. So it's fairly straightforward, fairly easy to get it right, to control what you need to control, and to provide the services that you need to provide. And as you can see, there are, like I showed, there are the examples already commercially available, and you can do it pretty in a pretty straightforward way. Next slide, please. But there is a big potential here to apply the same technology, the grid forming technology, to farms as well. So far, like I said, most farms, almost all of them, are grid following, meaning that they need to get connected to a relatively strong grid, a capable grid that can give them that point of connection voltage so that they can extract the frequency. But it's very cost effective if we can apply grid forming capability to farms as well, because you literally don't need to change anything. The farm that you've got there, which has problems to get connected to weak grids, if you equip it with a grid forming capability, you can then suddenly make it grid forming, and you can connect to very weak grids. Not only you won't be a problem, you will be a part of the solution. But there are certain problems, there are certain limitations that we need to find solutions for them. Basically, the main problem here is that you don't really have a fixed DC voltage that battery is giving you. The battery, your energy side, the DC side, is not really decoupled from the grid. And particularly because you're very much operating point dependent, your farm is very much operating point dependent, the energy that you're transferring with the grid, the rate of change of energy is not really an easy thing to control. Like I said, it's very much operating point dependent. Additionally, the DC link is not constant. You don't have a battery that would fix it for you. You need to control the DC link voltage. Assume that you've got, for example, a wind farm. You've got 2 inverters connected to your turbine and connected to your grid. The DC link between the 2 needs to be controlled. The rotor speed needs to be controlled. And also black start capability would be problematic. It's not an easy task. So these are all the challenges and problems that we need to overcome before we can make wind farms a reality in our grids, grid forming ones in our grid. Next slide, please. There is one example that you can probably read more about in the paper that I put at the bottom of this slide. Siemens Gamesa in Scotland, they operated a Type 4 wind turbine, including 23 full converters, 69 megawatt for 6 weeks back in 2019 in VSM mode, virtual synchronous machine mode. And they tested so many different scenarios. I guess the details of this you can find in different literature around this particular farm, which is a very good, I would say, example that showed that there is a possibility to apply grid forming capability to wind farms. But obviously, there's many limitations still exist that needs to be overcome before this can be a commercial reality, particularly when your wind speed is declining, the turbine ability to respond is affected, zero power output, you've got a lot of difficulties, to operate. The grid forming capability would require certain energy in your system to be able to react. So there are still a lot of challenges around that, but there is one example, which is great, at least to see that this is possible. Next slide, please. So at Monash, we have started working on this technology, and we have started developing a control system for implementing grid forming capability to type 4 wind farms. They've already started doing simulations on a typical type 4 wind farm. We have taken a grid following one, and we have designed the required controllers for the wind farm to become grid forming. And we've started doing quite a lot of tests, starting with MATLAB Simulink and PSCAD. So we first obviously started with the grid following capability to understand how it works. Then we applied grid forming with Droop based, and then virtual synchronous generator based, VSG that you're familiar with. We then applied a control system that we have developed at Monash. We call it compensated generalized VSG. We applied that technique as the grid forming capability to see how things would work. And then we are starting now to test it in many different scenarios, larger systems. We started obviously first with the SMIP case. Now we're applying larger systems, IEEE 39 bus and hopefully Victorian system, a Westmire region in PSCAD. So we're hoping to apply to those cases and understand how the system would work. Next slide, please. Here is a brief overview. Obviously, we won't have enough time to go through the details of these blocks, but this is one part of the control system, the grid side converter. It does require to control the DC link voltage. It does require to control the rotor speed, and obviously provide all the services that you would require as a VSG. So the primary loop here, voltage loop and current loop, are pretty similar, but still there are there's certain differences between these blocks and a normal VSG, but the capability is the same. So it can provide inertia, it can provide the damping that you require, and it doesn't require any PLL to be connected to the grid. There are also other block diagrams that I haven't shown here for the machine side. So you need to also do a lot of different controls at the machine side, there are certain differences between that and a typical grid following farm. Next slide, please. So here are certain tests, some of the preliminary results that we have obtained. So we are showing here the Droop VSG and CG VSG, the one that we have developed at Monash. Particularly, I would like to talk a little bit about VSG and CG VSG. Droop will not give you the inertia that you would require. The test conditions here, SCR5, XR ratio 5, and the deloading factor, meaning that we have deloaded the wind farm in order to give us headroom to operate. And then the events that you're looking at here is a frequency jump, so a 0.1 hertz frequency jump, and we are looking at the performance of these different controllers. And as you can see, the CG VSG that we have developed has a pretty nice smooth transient, even when we are having this pretty harsh test, 0.1 hertz frequency jump, which is pretty actually harsh. But it still can very nice, smooth recover from the fault, from the transient. And this is still work in progress. We're hoping to work more on this and develop further, but the preliminary results are pretty promising. We have been able to eliminate the PLL. We've been able to provide the services that we would like to provide, the inertia that we would like to provide, the damping we would like to provide, and the transit is very smooth. And one challenge, by the way, that we've got in wind farms is to make sure that the torque that is requested from the turbine is not seeing any excessive transients, because it can cause some mechanical problems for the turbine, some fatigue problems. So we need to also make sure that all the transients are within the capabilities of the turbine from a mechanical point of view. And the current controller that we have developed is actually, particularly the CG VSG, is meeting all of those requirements. But still, it's work in progress, and we are still working on this. This is, I guess, a research project for us over the next couple of years. We need to fine-tune quite a lot of different loops and blocks in this. Next slide, please. So future works for us, enhancing the compensated generalized VSM technique for farms. So far, like I said, the preliminary results are pretty good, but still we need to enhance that. Particularly, we are keen to work on the startup procedure for wind farms using this grid forming capability. And also analysis over the internal instability of these when we are having different problems, unwanted wind turbine outages and things like that. So this is another thing that we need to understand, how those blocks that we are developing and designing might become unstable. And also evaluating the appropriate deloading factor. The deloading factor is extremely important because obviously you don't want to sacrifice much of your energy that you could generate to provide this grid forming capability. This is another thing. And also extending these to solar farms. We've started with wind farms because it was more interesting and more challenging from a research point of view, but quite a lot of learnings can be applied to solar farms as well. And we could hopefully look into them and understand how they could operate. Thank you so much. I guess that concludes the presentation.
Thank you, Beru. Before we introduce our last speaker, just want to remind everyone that there is an option to ask questions in the Zoom Q&A function located at the bottom of the screen. We will be sourcing questions from the crowd in the final Q&A panel discussion, so feel free to chuck in your thoughts there. There's also an option to upvote questions from other attendees. So finally, last but not least, we have Nigel from TransGrid. Nigel is the General Manager of Infrastructure and Energy Services at Lumia and is responsible for leading the investment and development of renewable energy assets. Over to you, Nigel. Nigel, I think you're on mute.
Good start to my morning. Thank you, Gina. Good morning, everyone. I'd like to start by also acknowledging the traditional owners of the land we meet on today. For me, that is the Gadigal people of the Eora Nation. I'd like to extend my respects to elders past and present, and also extend those respects to any traditional owners with us today and traditional owners on other lands and meeting on other lands today. With that said, I'd like to thank the previous panelists, as they will probably save me a little bit of time as they've covered a lot of ground already. What I want to talk about today is wall-growth BESS. You've heard about a number of batteries, but what I'd like to talk about is this battery and why it's different and what makes it different from what you've already heard today, and then focus on the commercial aspects of batteries and the unique contracting structure that was developed for this battery. Next slide, please. As a quick overview, the wall-growth battery, what is it? Why does it exist? Why did we choose to do it? Fundamentally, we did it with ARENA and New South Wales government to enhance reliability, deliver more affordable power, and increase the knowledge base. And you've already heard today about the work ARENA's done on a number of projects to deliver better knowledge base to enable the transition of renewables. Wallgrove is the first grid-scale battery in New South Wales. It will also be the first VMM-operated battery in New South Wales, subject to some final approvals and activation in July this year. What was the battery designed to do? Well, it provides new sources of system stability and services. You've heard a lot about that today already. It's about finding the lowest cost way to deliver these assets. And there are a number of commercial models that enable low cost delivery of these assets. And each of the projects you've heard about today have slightly different models depending on the customer, the basis, the investors behind those projects. Obviously, I won't speak to other people's investments. And it also provide valuable technical and economic insights. And I'm pleased to hear today that the Darlington Point battery and Edify battery has had a smooth run through the GPS project. I think it reflects the work of both the Hornsdale battery, this battery, and batteries in Victoria to get us to where we are today. And that is a huge thanks to ARENA, their funding and the programs they run. Wallgrove in its essence is a 50 megawatt, 75 megawatt hour battery with a counterparty contract with Iberdrola to manage contractual risk. But before I get into the contractual risk, I'd just like to talk about its uniqueness. And if you can move on to the next slide for a pretty picture, which I think you skipped one. There should be a slide before that. That's it, thank you. This is a picture of the battery. You've seen pictures of batteries before. What's interesting about this picture is actually not what's in the foreground. It's what's in the background. It's TransGrid Sydney West substation. This is in Western Sydney. It is the largest substation in the Southern Hemisphere. And why this is interesting is most of the batteries you've heard about today are on the generator side, but not surprisingly, the services that batteries provide and inverters provide and grid inverters provide are needed on load side as well. And so sitting next to the node, the centre point of the grid for New South Wales, has meant we've been able to work collaboratively with TransGrid, LMEA, New South Wales Government and ARENA to develop unique structures and unique operational conditions for testing the capacity of this battery to support grid issues on a load side location. In the technical sense, hopefully you've all by now read the slide. You can see 36 Tesla megapacks seems to be the preferred technology for today. Interesting contract with the OEM, but I'll get onto that in a second. Usual primary plant transformer, transmission line, loops around to what's not on the screen, the left-hand side, and comes into a bay amongst many bays into the TransGrid West substation. So that's the technical overview of the battery. I will not talk technically. My panelists well know I am not a technical person. I'm more a commercial and contracting person. If you could go to the next slide, perhaps that's the best way to describe the challenge of new technology on the grid. The slide's interesting, but perhaps the most important part of this slide is two things. What's not on it, and why is it so complicated, and why does it look like a spaghetti diagram? Well, the simple answer to that is Wargrove was designed to test a commercial market model that enabled the revenue stack of batteries with support from ARENA, New South Wales Government, TransGrid and LMEA as a commercial entity. That's the four things that aren't on this slide are the investors. Running through them quickly. TransGrid invested in this asset as a regulated asset base to provide funding for use of services to support the grid as part of the evolution of the network and to understand how a system like this would affect the grid at a load side of a major node. LMEA invested in this battery as a commercial proposition, recognising that there was a gap in funding, but also wanting to test how you could bring together revenue stacks to deliver a successful commercial project. New South Wales Government, ARENA, as always, supporting development, evolution, enabling that transition to align with the objectives of both the federal government and the state government in New South Wales in this case. What's interesting about this diagram coming down a level is how the contracting structure worked and what we learned from it. Iberdrola is our counterparty. They are trading the energy. They are buying a service out of the battery. So rather than a traditional battery where usually the owner is trading energy as part of their energy portfolio, it's usually part of an energy trading hedge or an energy market model. In this case, that was a service contract to a third party run through a commercial project to maximize the value of the battery across the whole energy spectrum and enable a solution that in essence enable multiple use of the battery for multiple commercial and regulatory purposes. On the other side of that is the regulatory use and the commercial construct we had to create to enable a certain allocation of the battery to be reserved and the inverter technology and grid forming capacity to be available at the right times for the systems that the network needs, despite the commercial use of Iberdrola. That's kind of the overview investment. At the operational level, quite interesting from a risk allocation point of view. At the time we did these contracts, the financing market was rightly cautious about splitting contracts. And so as a result, we have a wrapped D&C contract with Tesla as our O&M. And Tesla took on the burden of the balance of plant, the substation, the transformers, all of the components of that to enable the correct risk allocation at the time. Interestingly, the projects, one of the learnings of the project is it has identified that the right-hand side of this drawing probably could be simplified by allocating risk to the correct party to manage that risk. And if I explain that quite simply, if you think about the contract, is an OEM provider the best party to manage balance of plant, transformer, high voltage kit? Probably not, albeit they're more than happy to do it, did a great job of doing it. The question is, what is the best allocation of risk and capability to the contractors? Tesla has a view on this, we have a view on this, but I think one of the learnings out of this is about how you correctly allocate risk and what we would do differently going forward. You can see in the bottom, in the middle, the pre-commissioning, the market registration, the process that was required to get the GPS through. We probably complicated it more than most by having a separate market participant, ourselves as the developer, and then TransGrid in the role of the grid regulatory space. And so that GPS process for us was quite challenging, the bit in the middle where market participants were involved, market registration, because it added a layer of complexity. I guess, as Sam has already touched on, it wasn't so much that the rules didn't allow for this or couldn't cope with this. It was more a case of taking everyone on the journey, developing the project in a way to a new model and making sure we were able to transition that process with AEMO and regulators and ensure the separation between the regulatory assets and the commercial assets. Chris has already mentioned from AEMO that there's a bunch of iterations about to come out and guidance on how to navigate these paths. But if I was to reflect on what we did here, I think we probably would have started some of those discussions sooner and made them a more fundamental part of our contracting structure. And we've done that going forward on batteries, and our lesson learned reports speak a little bit to, that are available through the ARENA website, speak to those challenges and those commercial challenges. I'm not going to dwell on the technical aspects of grid informing inverters, but ultimately what this commercial structure and interplay does is enables all parties to get what they want out of the battery for their purpose. And I think Sam summed that up pretty well by saying, if you start from a place of what the network needs and also a place of what your customers need and what the energy market needs, and bring those two together, you can find commercial solutions that will suit the particular case. In this case, the benefit of the regulatory asset and the commercial asset together was to demonstrate an investment model that is a little bit different, but maximizes revenue from the various market services that were available at the time of this battery. As the market evolves, they will change and the commercial models will change with them. You can see already commercial models in today's discussion that are subtly different. Hornsdale will be different because it was earlier than it was for Edify and Riverine. Eventually, we will reach the right stabilised state for risk allocation. But I think the most important part of this project, beyond the technical aspects that have already been talked about, because they are in some respects similar to what you already heard, has been about how you can make the regulatory framework and the challenges of the different funding mechanisms work together with an ultimate aim of driving towards a commercial solution that enables this technology, like other technologies, to be delivered without funding. And we are optimistic that that is possible relatively soon. If you'd asked me in January this year, I said it would have said it was absolutely fundamentally possible. But market dynamics have changed a bit since January, and so we're at a really interesting threshold in the market, albeit they are fundamentally still viable to support what's required in the NEM. You've already seen the chart from Elise around what's required to transition the removal of carbon and gas technologies from the market. If I could have the next slide, please. So with all that said and kind of gone around the spaghetti diagram myself, without going into specifics, what did we learn from the project? I think that's probably the most important thing to share in this audience is, whilst the technology is evolving, the technical issues are being worked on by the incredibly talented people, some of whom you've already seen today. What did we learn out of this project, and what is the benefit to the industry going forward? Well, it was a success is the first point. It went commercially operational in December 2021. You can go and look up the trading that's occurred across it by Iberdrola. It's been very successful, been supported by some volatility events. Some extended market volatility has helped the results commercially because that changes the pricing points. It is operationally available. The charge and discharge profiles match what we're expecting, and the virtual machine mode is expected to be implemented in Q3 2022. So that's everything that went right. We're on time, mostly delivered it to budget, and delivered a project that enables us to test all of the commercial contracting structures, as well as test the use of the technology in the inverters at the node end at the Walgrove. What were the challenges? There are a few challenges. Grid connection approvals I've already touched on. They were a challenge for a combination of reasons. They were a challenge because we started in 2019 and we're all learning how these technologies, GPSs all came together in the model. And there's a number of committees and groups, and AEMO in particular, who worked very hard to make that easier and smoother. So we now find ourselves in 2022. A lot of that knowledge is now being seen in the processes that others are being involved in, which is great news for the industry going forward, because it should improve the time with which it takes us to get these things up. And also Hornsdale has been a huge part of that evolution. We had some registration challenges. Having an investor that is the TNSP complicates things. Having a energy trader as your registered participant means an extra set of approvals. We always thought the challenge of doing that was worth it to demonstrate the variety of commercial models that can be used to deliver not only batteries, but other technologies in the NEM and the regulatory framework we have today, and also influence potential changes to that regulatory framework as necessary as we go forward. And I won't speak to the various reviews that are underway on the market design and market. I'm sure most of you are aware of them. But a key to all these changes is about the services that we don't have once traditional generation falls away. And really that is all about the things you've heard about. And the grid inverters are a huge part of this, and battery grid inverters, we've heard about them role in renewables as well. Ultimately, all of this collaboration is the key. And I can't speak highly enough of how much our OEM, Tesla, lent into the challenges of our contracting structure, and how much the regulators helped us get through this process, albeit we would have all liked it happen quickly. I am being told I need to hurry up, so I am going to wind it up because this is my last slide. The other part I've already touched on, which is the market changes and the market volatility. I guess looking forward, what does this tell us about batteries and how do we make them commercial and at lowest cost to consumers, which is where we started? Well, a lot of that's going to depend on the design of the market, but also on the volatility coming out of the market that we've seen in the last 6 months. All projects are challenged by the global supply chain market at the moment and challenged by increases in commodities pricing. That will impact the market for a little while, but should then stabilise to return us to a state which, on the back of a project like Wellgrove, we absolutely 100% think in Lanier, we will be able to deliver 100% commercial battery that will be the trigger point for where batteries are a known and dedicated technology that can be delivered. Until we get there, we're going to continue to need some support from government and ARENA, but I think this Wellgrove battery has been a huge case of the industry working collaboratively together to deliver not only technical outcomes, but commercial and consumer outcomes that reduce costs to consumers. I'm going to stop there to allow people to ask questions and roughly stay on time. Thank you, Gina.
Thanks, Nigel. Appreciate it. Thank you, Nigel, for that presentation, and thank you to all of our presenters today. It has been really great to hear such a diversity of perspectives and thoughts across industry, and the content has certainly been thought-provoking. So without further ado, I suppose we'll now proceed into our Q&A discussion. Those who are listening in on the line, please feel free to continue to ask questions or upvote questions that have been put forward. So the first question that I'm going to throw to our excellent panelists is one that has been quite upvoted by the attendees here. When inverters are operating in virtual machine mode, is power headroom required in order to provide the synthetic inertial response, so the asset is not able to bid its full power into energy FCAS markets?
I guess that one's primarily for me. This is a topic that keeps coming up, and I guess it's one that's needs to be discussed as an industry. But there is some overload capacity available on the batteries, and also we're kind of operating in the amount of time you're operating in kind of at that peak. Power output is quite limited. So there needs to be discussion on whether there's some kind of power reserve for inertia, or whether or how that's dealt with. And that's an ongoing discussion.
I think commercially, from my point of view, Wellgrove, we had to look at how you preserve that capacity in a contractual sense, to leave headroom or otherwise to meet the needs of the investors and the counterparties. I think Elise is absolutely right. There's a wider discussion needed about what the right model and preservation is. And there are various projects in the market at the moment. Everyone will be aware of big batteries generally being delivered by state governments, and that both the commercial contract construct as well as the technology interplay that Liz is speaking to will be absolutely critical to making sure we get the best system outcome as well as the lowest cost outcome.
Yeah, I might also chip in there. I think we've looked at this, I guess, specifically for the Darlington Point BESS and done some studies on it. And I think it does depend on what you're trying to achieve. I think if it's just a frequency response, obviously you need active power and headroom is required. But I think what we've found is if you're just trying to stabilize oscillations, it's not that active power element of the response that's critical. And so we've shown that, I guess, regardless of the starting state, even the battery operating at full output, you are able to have that dampening impact on oscillations.
Thanks, panel. The next question we have is, are we going to need wind and solar PV with a small amount of DC storage, regardless of whether the BESS is supercapacity or small, to allow for grid forming?
Well, I can probably give a short answer to this. Obviously, having a battery energy storage in parallel with your farm would definitely help, depending on what exactly you expect from it. But yes, you can have battery energy storage in parallel with that, and that's, I think, probably the very the easiest way of providing this grid forming capability, because then the battery can be in charge of grid forming, and then the rest of the farm can follow the battery and then be in the grid following mode. But you can also remove the battery, and what I was showing in my presentation, we didn't have any battery involved. We actually modified the controller structure of the farm itself to provide the grid forming capability. And in order to achieve that, we had to deload a little bit. We had to deviate from the maximum power point of the farm, which is not great. So you're producing less energy, but you can make sure that you have grid forming capability. You can make sure that you can operate in very weak networks without any stability issue. So I would say this is a trade-off between what you want to get out of it. If you're going to get the stability and the security for that region that you're operating with or operating in, or whether you want to achieve the maximum power point. So if you're going to achieve the maximum power point, then grid forming capability for the farm is not the way to go. But if the idea is to, yes, provide, generate quite like 90%, 95% of the capacity, but still give the grid forming capability as well. If that is the objective, then yes, we can go with grid forming for farms. But in terms of batteries, yes, you can have the batteries as well, but it's not necessary. So you can provide a grid forming capability without having those batteries installed.
Thanks, Meru. I think that's a great segue into the next question on batteries. How does operating in virtual machine mode impact how you can charge or dispatch your batteries? Big question.
So I think in one of my slides I showed like the machine response to one of the disturbances that we generated during hold point testing, and you can see in those responses that the virtual machine mode response is often kind of like a spike, and the time scale is very different to the time scale of energy dispatch or contingency FCAS responses. So we see these being able to act kind of simultaneously but on different time scales. And so thinking about them separately as the fast occurrence grid stabilizing features compared with the kind of market features on a longer time scale.
Thanks, Elise. Another question, moving away from batteries this time. What would a grid forming inverter solution for a solar farm look like? Would you need to connect a battery on the DC side?
I guess this is again similar to the previous question. Yes, you can install a battery at the DC side. Obviously, it will help with a lot of things. It will help you with the DC link voltage control. But again, it is not mandatory. If you want to deliver the services that a grid forming inverter want to deliver, you can use a solar farm without having a battery. Yet again, you need to deload the farm to deliver those. You wouldn't be operating at the maximum power point. If that's not desirable, then yes, obviously we can install a battery at the DC side to help, or a battery in parallel with the farm. I mean, a grid forming inverter in parallel with the farm to help and assist, I guess, in some of the presentations we saw that, and that's normal, and that is already being done. Having said all of these things, yet grid forming technology for farms not a commercial reality, and I believe there are quite a lot of things that needs to be resolved, a lot of questions needs to be answered, and a lot of research needs to be done to make sure that we are getting it right and we can deliver what we're supposed to deliver, and at the same time generate enough energy to justify the farm itself financially.
Thanks, Beru. The next question is a little bit less grid-centric and deviating from a lot of the subject matter today. What are the panel's thoughts on the rollout of grid-forming inverters through the provision through distributed energy resources?
Could have a go at that. There's probably a couple of angles to consider, though. Are we talking about distributed resources from the perspective of larger grid forming plant deployed in the distribution network, or are we talking about sort of household level DER? I think for the former, I mean, a lot of the distribution network and a lot of batteries of the sort of the tens of megawatt scale are very much looking at that as a space to connect. And so I don't necessarily see that all that different a case from the, say, the larger scale transmission connected plant, other than they potentially are facing a higher impedance, which could influence their ability to deliver on benefits, I suppose, from their grid forming technology. But certainly that's still a space that's of interest. I think when you get right down to household level, this gets a lot trickier, right? You're now talking about a grid forming plant that is designed to remain online and support the power system during disturbances, and yet is also required to comply with anti-islanding restrictions. It's not supposed to stay online during some kinds of disturbance. You've also got the challenge that sort of household inverters are typically single phase, so you're trying to sort of support the grid from one phase at a time. But to kind of counter that and to talk about why that might be interesting, I mean, we're seeing these incredibly high predicted, renewable resource availabilities as early as 2025. And some of those earliest periods are actually heavily driven by DER, sort of, 60, 70% of consumer load being served by DER at any given point in time. And that grid following DER isn't there to support and stabilize the system. So if there's a way to kind of nurture that part of the fleet, which could be a majority at particular points in time, that's certainly of interest, but I think quite challenging.
Thanks, Chris. Any other thoughts from the panel on this one? No, all good. Going back to the grid then, one person has noted that the Hornsdale Power Reserve hold point testing utilised a nearby wind farm power to demonstrate its performance. So how else is hold point testing being planned for other projects where there may not be a nearby large power TF available to be switched off and on again? It's a good question.
Yeah, I can start with that one. So for hold point testing, bringing on any new generator typically requires doing that similar kind of test, in that you have to create a external voltage disturbance to show the plant's response to that. So that's not a new thing for the machine response. I guess what does differ a little bit is that we want to make sure that voltage disturbance we create is substantially larger than the noise and is big enough so that we can show in a detailed model what the virtual machine mode response is doing, which is a bit more difficult than typical. So yeah, this has to be assessed on a site-by-site basis. I know like Wargrove being next to a large transmission substation, it might be easier to find kind of capacitor banks and lines to switch to create that disturbance. But yeah, it really needs to be assessed on site by site.
Yeah, I think from our perspective at Darlington Point, I mean, I think it's important to recognise that there is sort of two levels of control that are being looked at here. One's the PPC level, which is sort of the plant wide, which can still be tested using like reference voltage set point changes. It doesn't need an external impact to assess it, but the actual inverter level control typically does need some sort of external disturbance. I think there are the two elements that you need to test, and that inverter level you probably need to look at some external disturbance. We're thinking about transformer tapping, whether that will provide a big enough disturbance to see a response and analyze that. But yeah, otherwise you need to look at other network equipment.
Thanks, Elise and Sam. The next question we have is, are we going to need to manage real-time megawatt curtailment to allow for inertial type responses?
I believe this is for farms, if I'm not mistaken. And yes, so we need to have that curtailment. We need to have a deloading factor in the farm in order to be able to provide that service. This is one of the challenges that we've got in that controller that I showed. We are still working on that. We're still working on that deloading factor, that how much is required for different operating points and for different levels of inertia that we are hoping to provide. So that's still for us an open question. But yes, we need to sacrifice some of the amount that you could generate if you were operating at the maximum power point to deliver. But having said that, you probably can, and this is still, again, it's still work in progress, but you probably can change your your inertia constant in order to provide less inertia to the system and go back a little bit towards the grid following mode, in a sense, not providing those services. At least it will help you to operate in a weaker grid. But yes, yeah, again, long story short, you need to sacrifice some of your real power.
Sarah, I just wonder if, well, sort of explore that question and some of the other ones that I see in here from the perspective of kind of reserving headroom, and or taking advantage of overcurrent capacity, which I guess I see as a sort of a similar space. With reference to a battery, I guess that's taken from the perspective of, how can I kind of optimize as the owner of that battery, the use of that asset without having to retain unused potential from it. And ultimately I see some questions in there around it. How might you be remunerated for that? Interesting answer from you before, I think, Sam, around if you're looking to kind of provide system stability, it's not necessarily the case that a lot of headroom would need to be reserved. And I guess it's a bit of an open question as to how much active power capacity would be needed in your back pocket in order to provide things as like inertia. This is one of the really key questions that I want to explore in the development of this sort of voluntary spec process, because I see there's quite an overlap here between what would classically have been seen as a sort of an operational aspect of where's the operating point of your plant versus a connection aspect of, well, how do you demonstrate the capability that your plant has? And so there probably is a little bit of overlap there that I think we'd welcome a lot of discussion on.
Yeah, I mean, and to chip in to start there, Chris, I mean, I often think as like the active power and reserving that, it's almost like the need of that for the network is for frequency control. And there already is quite a well-defined, I guess, mechanism in the market with frequency response and the trapezium, where you can bid in energy or you can bid in frequency response, and the sort of the trapezium prevents you from sort of bidding in both when you can't provide it. I know inertia is probably, I guess, a little bit grey at current because it's not currently considered in the traditional frequency markets. But perhaps that's something that is best addressed by bringing that into sort of a fast frequency response type market, or an inertia market as such. And then again, you sort of managing bidding between energy and sort of frequency inertia type markets, rather than sort of having this blanket requirement where we're reserving headroom, because I think it is quite distinct from the other function of grid forming inverters and sort of providing system strength, which I don't think requires that headroom to be reserved.
Could I be bold to ask a follow-up question on that, Sam? If you go down that path, I guess the question that arises is the secondary part of the market dynamic is the allocation of ultimately liabilities related to the grid stability. And so there's this tension between the market services and the liability that evolves. I'd be curious to know how Edify and others are thinking about that.
Yeah, sorry, Nigel, could you just repeat that? I just had my speaker drop out for a second.
No worries. The core of the question was, as you evolve the market side of your revenue stack and open up the market capacity inertia, the services we don't currently have as market services, how does a developer like yourself think about the liability side of that, and how you find the balance between the obligation to keep the grid up, which currently lies with the NSP, and the revenue expansion of the stack to make the project work? I was just curious to know how a developer thinks about that. Obviously, NSPs and think about it, but I was just curious to understand your thinking on that.
Yeah, I mean, I guess our perspective is we're not currently contracted to provide any sort of network services, and I think to the extent we were, we'd expect there to be some sort of formal contract in place to provide system strength services. And I guess, yeah, the regime around availability, non-performance, non-provision of that service, and sort of associated LDs with that would be dealt with in that contract. Yeah, and we look at sort of the robustness of the plant, confidence in providing those services, and considering sort of that contract at the time.
Yeah, interesting. I mean, ultimately, it's a market design question that there's a lot of work being done on about what the right allocations are, but really relevant to making grid inverters and this technology lowest cost. But happy to talk further offline, Sam.
Yeah, sure. And look, part of our thinking in doing these grid forming inverters is, I could say, it's a new market, but I think some of these revenue streams and contracting ideas haven't yet sort of materialized or haven't yet become mature. So look, I mean, I think, but it's an opportunity for future revenue streams for these projects, and it's, yeah, these generators are going to be connected for 20, 30 years. I guess possibly with the replacement of batteries, and so having a technology that's going to be robust and can be tuned for the next sort of period of time is very critical to our thinking.
Yeah, I guess in the end, we're probably not going to have one commercial solution given the extent of the grid.
Yeah.
Thanks, Nigel, and thanks, Sam. There's been another question as well, similar to this line of thinking, and I'm going to put Elise on the spot. Is the virtual machine mode a permanent mode? Does it always provide inertia, or is this mode selected at different times? Does it switch between grid following and grid forming to meet certain requirements?
Yeah. So I think that's a good question. Just to start, yeah. So it is kind of switching between grid following and grid forming, in that under normal network conditions, it's just doing standard grid following, and then grid forming is subject to a disturbance being observed. I think, yeah, probably an interesting question though is enabling us to turn on and off virtual machine mode, and which stems to being able to change the settings of the virtual machine mode, so how much inertia is being provided synthetically. So currently, obviously for Hornsdale and TransGrid, we're applying virtual machine mode by running through a whole 539 update to the connection agreement. But I think in doing that and setting virtual machine mode on permanently under one inertial condition, we're missing an opportunity that synthetic inertia provides that traditional spinning generators didn't, in that we can change the inertia constant depending on the season or the network configuration, or adapt it easily as the network evolves. So yeah, I think that'll be a really interesting discussion moving forward as to whether we allow synchronous machine, virtual synchronous machines to change their inertia behaviors based on network conditions, and whether we can do that kind of through 534 process rather than a 539 and make it kind of adaptive.
So just to extend on that a little, we did call out in our engineering framework initial roadmap, you know, the potential value of being able to tune more readily, more easily, more quickly to suit network conditions, because the sort of the set and forget model of you lock in your tuning parameters at time of connection, and the grid moves around it from that point forward. It may not necessarily be the most sort of efficient way, and whether there are capabilities that could be deployed in the future in order to, you know, this isn't necessarily sort of real time or anything like that, but as the grid evolves over time, are there going to be easier ways to retune capability? I mean, if you extend that, would that work on a sort of an intraday sense? Are there times of the day where a greater capability is needed in terms of sort of, I don't know, inertial constants or sort of operating limits? And are there periods of day where that's less necessary or not desirable? So yeah, really interesting space to explore. I'm not sure that we necessarily have a path to resolution on that one, but it's an area of interest.
Thanks, Elise, and thanks, Chris. Again, on that thinking of grid following versus grid forming, another question that's been asked is, excluding renegotiation of network connection agreements and upgrading power electronics MDA ratings, how feasible is retrofitting grid forming / advanced inverter firmware and control on existing grid following resources? The age-old retrofit question.
I think it's probably a question for OEMs.
Yeah, maybe Tesla can answer that, but a very quick comment on that. From hardware point of view, I don't see any difference. So from hardware point of view, you should be able, if you've got a grid following inverter, you should be able to use the same hardware and just you know, change the control structure to a grid forming one, and that shouldn't add anything to the cost. But maybe, yeah, our OEMs can probably shed some light on it.
Yeah, I agree with that statement. So our inverters, we're using the original Hornsdale inverters and the inverters used in the expansion. So this is going back to inverters from 2017, 2018, 2019, where applying this new feature has just been a matter of doing the settings change. So yeah, definitely not a hardware change required from an OEM perspective. Yeah, in terms of how to do that easily, we did see it took quite a long time at Hornsdale to get through the 539 change to connection agreement, and there's been a lot of learnings out of that I hope can be kind of used to kind of make that process quicker. But yeah, I think it will involve, again, more industry discussions on how to make that streamlined and looking at whether a 539 is essential in every case, or whether we can look at doing setting change through the 534 process.
I'll ask a follow-up on that one, which has been asked to me and I've not been able to answer it before, around because I largely agree. I mean, if it's an algorithm change, if it's a firmware change to go to grid forming, that would seem as though a retrofit would be quite comfortable. But I guess, are there sort of system level, plant level decisions that you would make during the design phase if you were producing a grid forming plant that you might not necessarily make when developing a grid following plant? And by that I mean, for example, if you wanted to oversize the inverter capacity, that would obviously be a hardware change in order to maximize your capability to deliver on those grid forming capabilities. But you know, if you go to retrofit an older plant that maybe wasn't designed with that in mind, might you be left with a less capable design overall? Open question. I'm not sure if there is an answer to that, but I've certainly been asked that a number of times.
Yeah, I mean, I'll jump in, Chris. I think, I mean, certainly you'll be limited to whatever your hardware and your balance of plant sort of is installed there. I don't think there'd be significantly a significant difference between the setup you'd go with if you were designing for grid forming. There is a bit of overload capacity in our grid forming plant design at least, but it's not this significant amount. I think you would still get a lot of benefit from bringing on sort of converting older plant to grid forming controls even without that overload. I think you'd get 99% of the benefit of doing that without sort of increasing the overload.
Sure.
Thanks, all. Going back to this idea about switching between grid following and grid forming, there was another question from the crowd that asked, has there been any consideration to enable or disable grid forming mode based on grid conditions? So, if the grid moves from a strong to weak state due to element outages.
Yeah, there hasn't at this point been the discussion because the agreement is based on a certain inertia constant in the settings. But yeah, I don't see a reason why moving forward that shouldn't be a big topic of discussion, and looking at adapting whether we can kind of turn the feature on and off, or probably more realistically change the parameters to give a larger or smaller inertia response based on the grid conditions.
If I may add something here, it is possible your inverter to identify the grid on the go. So when you're connected to the grid, there are mechanisms that the inverter can identify the stiffness or the impedance of the grid to which it is connected. And if you know that impedance, if you know how stiff the grid is, if you know what is the SCR, and if you know the impedance of the grid to which you're connected, then you can potentially act on that and change the parameters of the grid forming control in order to provide better performance. Because when you design a grid forming control for a given grid strength, then if you change the grid strength dramatically, or not even dramatically, if you change it, then the performance wouldn't be optimal. But if you know what is the impedance at any point in time, then you can act on that and change some of the parameters in your grid forming inverter in order to provide better performance. So it is possible, and it comes at a cost of doing certain identifications in the network to understand where you're connected to, and whether something changes. But typically, when you connect to a point of connection, the SCR is not going to change dramatically. Often there might be changes, but not dramatically. So often, when you design for a point of connection, that design is typically good enough for surroundings of that point, that grid strengths that you're connected to. So it is possible to adapt. It is possible to adaptively tune, and it all depends whether the grid strength is supposed to change significantly or not.
Thanks, all. Moving away from the technical spec sides of things, I'm going to ask a question around interaction with the grid and network. Got a question from the crowd. How does active power from grid forming services, specifically inertia responses, interact with active power dispatch targets in the spot market? Would the BESS be subject to receiving penalties for potentially missing dispatch targets?
Without knowing this precise answer to this one, I'd have to take it on notice, but is there a difference in this scenario between a grid forming battery and a, say, a synchronous machine that would also be exhibiting inertia and participating in the spot market? I would hope that they could be treated the same.
Yeah, look, I think from the Darlington Point perspective, I think we'll follow, the plant will follow dispatch targets. If there's a low frequency, that there may be some inertia response that causes an increase in active power. You don't get penalised for missing your dispatch target in that respect, though, because you're providing a benefit. I think the mechanism through kind of measuring whether you're having a negative impact is through causer payers generally. But as long as you're responding in the right direction, sort of and in accordance with your primary frequency response, you're not penalised for missing your dispatch targets, providing an inertial response.
We do have a project recently funded by ARENA actually to look into developing a market for grid forming inverters and inertia, virtual inertia market. which potentially can look into these aspects of things as well. And that's actually an interesting question that potentially that can fit into the larger picture of a market for inertia, that how these things can be taken into account, and how not to penalize or how to incentivize certain services in the interest of the network.
Thanks all. I suppose continuing on the interaction with the grid, another question we've got is, what was or is the best response time for grid forming batteries at the point of connection? For voltage fluctuating at a very low frequency, would it be able to respond faster than 2 seconds?
Yes, it would be able to respond faster than 2 seconds. So the timescale typically for a kind of virtual machine event is sort of the 100, 200 millisecond response. So yeah, it's for a frequency event, it's responding before you exit the frequency deadband, and it's proportional to the rate of change of frequency. So it's very fast, yeah, and much faster than 2 seconds.
Just to build on that a little, one of the ways that we described in our white paper around, I guess, sort of response time and definitions around grid forming, and we'd sort of put forward this proposition that to be grid forming, it really needs that inherent response as opposed to a sort of a, you know, calculated react timed 2 second delay type response. And what I mean by that is if there's an internal voltage phaser within the equipment that is there providing a, you know, nominally 50 hertz sine wave, should a frequency disturbance or voltage disturbance, you know, apply to that plant, a voltage angle is going to develop between the plant and the grid, and naturally a current will flow. So that's a physics-based response rather than a, you know, sensed and reacted response. And that's, I think, something that we were quite keen to uncover, particularly through the development of the specification of, you know, is that the desirable line to draw as far as grid forming is concerned, an inherent response rather than a calculated timed response.
Thanks all. Kind of moving back onto the question around other technology types that aren't storage. Another question we've got is, many solar and wind farms are currently oversizing the DC capacity for their AC connection. Is there potential to use this overcapacity in the deloading factor when providing grid forming services?
Look, this is actually one of the aspects that we are looking into at the moment. We want to see what we can do with the DC side, and by not having a battery, but either having an oversized DC capacitor or maybe a super capacitor at that point to assist us with that. But this is an ongoing actually study for us. I don't have an answer to that yet, but my guess is that it should help. Having it, because, you know, well, obviously when you've got an oversized capacitor, super capacitor means that you've got an energy buffer there. So that potentially can help you to provide the services that you want to provide without actually sacrificing the maximum power point. But that's yet the study that we are doing. And we also very recently started a PhD project on this exact topic. So hopefully if we have the same webinar next year, I can have some concrete answers for you.
Thanks, Beru. We'll try to organize another one of these in a year from now, just so we can hear your thoughts.
Sure.
Another question we've got is that there's been a lot of discussions today about the role of grid forming inverters in, you know, emulating an inertial response and operating in drip-based response to inject and absorb reactive power. What other essential services might advanced inverters be able to provide? You know, how far can this technology go?
We had a couple of additional rings around that in our Advanced Inverters white paper, and I think I saw on one of your slides, Beru's, the sort of concentric circles diagram of, well, okay, once you've got a device that can support system stability, can it do so, for example, on a subsystem island in conjunction with other resources? So that sort of support a smaller island. The likelihood of you in a very high IVR system, the likelihood of an island forming that has only IVR on it is up. And so I guess it's at some point we need to consider ways in which grid forming batteries probably can support subsystem islands. The larger ring around that, which I think is actually something that we're quite interested at, in the near term, is what are the system restart support capabilities from grid forming devices as the synchronous fleet mix changes, exits. We need new sources of system restart, and so that's one of the actions that we've called out in our priority actions report in June this year.
Fantastic. Look, unless there are any other questions from the crowd, and I'm going to quickly use this moment to let anybody pop you any other questions. I think that concludes our Q&A discussion. As great as this discussion is, it is lunchtime soon, so might actually wrap up early and give people a few minutes back in their day. Thank you to all of our wonderful presenters today for their insightful information and from the great questions from the audience as well. It's been a really diverse discussion. Thank you also to my excellent colleagues, Lisa, Lim, and Andrew, who have been helping out with the tech in the background. Really appreciate your help there. Again, we will be posting a recording of this webinar and a summary on our knowledge bank soon. You can access an array of reports, studies, and tools and nerd out on all things clean energy via our knowledge bank. Finally, and last but not least, Lisa will be dropping a survey link in the Zoom chat box for feedback on this webinar. And we'd very much appreciate those attending this webinar for your insights. So without further ado, that does conclude the formal proceedings of today's webinar. Thank you again to our presenters, and thank you so much for making the time to join us. That's it.
Thanks, Gina. Thanks, everyone.
Thanks all.
Bye-bye.
Thanks, guys.
Thank you.
Bye.